Thank you very much. Before we get started, a couple of quick words about who we are. Array Architects, we are a healthcare exclusive architecture firm. We have 8 locations around the country. By volume, we are the largest exclusive healthcare architecture firm in the country. In addition to the architecture piece of our practice, we also have Array Advisors and Array Analytics that are part of the platform that act as kind of a comprehensive service provider for our clients.
As the design industry continues to gather data, our ability to accurately predict the impact of exterior design options is exponentially increasing. Whether the healthcare setting is designed for a specific population, be it cancer care, pediatrics, etc., it must remain relevant to a cross-section of users. Exteriors can be designed to make a positive impact on patients, staff, and visitors. Some of the learning objectives we're going to take a look at today. We're going to learn and focus on the orientation-specific glazing selection and analysis within a building facade. We're going to look at methodizing complex exterior envelope geometries to help facilitate fabrication. We're going to take a look at some analysis of positive shading devices and how they relate to design for patient comfort in some of the public and waiting spaces. Then we're going to take a look at some conceptual cost payback analysis and energy saving strategies for projects. We're going to go through several projects. One, we're going to take a look at some passive response. The first one being a project in an urban setting. The second, a suburban model, and the differences between those two. We're going to take a look at some active responses, which is an active glazing system that we're designing currently for a Kaiser Permanente lab project. Then we're going to take a look at how to effectively communicate some of the cost savings to help clients make decisions relative to first cost, impact, and payback over the course of a project. Okay, so the first project we're going to take a look at is Emblem 101 Penn. It has an urban site. Effectively, it sits along Pennsylvania Avenue and Atlantic Avenue, which are 2 major avenues in East New York and Brooklyn. We're going to focus on the fact that urban sites have what I'll call compounding boundary conditions. So on a surface level, we take a look at each site, or this site specifically sits within its own block lot that has a predefined boundary line. There are multiple property types within that. For example, the lot has what's defined as a corner lot, a mid lot, and a through lot. And then within that entire property line itself, there's one tax lot with multiple zoning lots within that. To complicate this even further, urban sites typically have multiple buildings adjacent to it, whether they're across the street or directly abutting to it. This also affects some of the below-grade adjacencies, being where services are located, and if there are existing buildings, having to deal with issues of underpinning or adjacency and support from a structural point of view. There's also the impact of the shadows cast by adjacent buildings onto the property and how that affects daylight and positioning of fenestration on your property. There are also multiple yard types within that property. So there's side yards, which have their own setbacks, front yards, which have slightly different setbacks, and rear yards, which all help to define the massing of the building itself. In addition to the adjacent buildings and sort of the definition of the property itself, we have multiple transit adjacencies. We have 2 major rail lines, one directly below grade on the west side of the site. That's a New York City metro line. The other is the Long Island Railroad, which is underground directly under Atlantic Avenue. When we deal with mass transit, large moving metal objects below grade, we have easements that we have to stay away from below grade, but then we also have issues that we have to concern ourselves with, being vibration and magnetic field interference. In addition to that, to make things even more complicated from a pedestrian and traffic point of view, we have additional boundaries of bus routes. We have stops on 2 sides of the building. All of these adjacencies lend themselves to sort of limiting access and providing sort of constrictions and opportunities for access around the site. There are existing curb cut conditions that we have to consider. Those can be changed or petitioned for change, but however, it's sort of limited by the number of curb cuts that you have around the site, so that begins to limit access to the building. And last but not least, there's existing tree plantings all around the perimeter of the building that we need to consider. They can be moved or relocated. A lot of times you have trees that have been there for 20, 30 years. Sometimes you don't want to move those trees. So as we start to understand the basic footprint of our building within the adjacent properties and the buildings around it, we can start to do some solstice and equinox analysis. So we basically take the dates of December, March, and June and project the time of day and the range and the shadow footprint to get a gradient of when the daylight on the site is going to be the highest level of impact. That helps us also understand how daylighting is working on the site relative to the heating and cooling days that are associated with the site specifically. We do this very early on to get an understanding of the initial impact of just basically the site footprint relative to the adjacent buildings and constructions around it. We can then start to take a look at different zoning scenarios for the site. So now we understand all the constraints around the site. We understand a little bit more about the property. As we start to define, first and foremost, how the building sits or the building orientation within the site, that helps us understand which facades get the most exposure in terms of daylight, an understanding of percentage of opening relative to adjacent property lines, and ideas about rating protection. If we're adjacent to existing buildings and we need to have portions of our facade either not have openings or be protected from a fire separation point of view. We can then take a look at the massing and zoning of the building. Once we understand those constraints, start to apply setbacks, the sky exposure plane, maximum heights, trying to max out the FAR, and then we can, within that massing, begin to understand building organization, where your access points are pedestrian services and vehicles, where is your core potentially located in relationship to those access points, how to maximize program continuity in relationship to where that core location is, and then how do you integrate mechanical and service entries so that they're done efficiently, but allow for pedestrian and vehicular access to sort of take priority within that relationship. From here, once we have a general understanding of the building mass relative to the setbacks and the zoning, we can start to do some early indication of solar analysis on the facades. We know that, for example, this site is located in a climate 4 zone. We know that per square foot, the range within that zone for a heating load should be about 40 to 50. That is obviously adjusted based upon final building type, latent heat, and equipment. However, in the early stages of concept design, we can take a look at this at a very high level. From there, we can understand the total building area and calculate out approximately what the BTU load for the building is. Now, this is approximately. When we start to take a look at this, we can then develop strategies for orientation, geometry, and positive shading. So these early indicators, for example, this is showing 177.8 BTUs per square foot. Just doing some basic math, we know that that is probably 3 times to 4 times the amount of gain that we're getting on the building. And this doesn't take into account glazing type, the shading coefficients of the glazing, et cetera. It's just the impact on the surface of the building. We know that this east facade, for example, has limited morning exposure because we know the daylight passes by it before it gets to noon. So we are essentially more concerned about maximizing visible light through this facade and less concerned about the heat gain on that facade in the early morning. Take a look at the north facade. We can see the north facade is a lot lower. It's actually in range. That's effectively a diffuse light situation over the course of the day, and that facade is predominantly in shadow most of the day. As we take a look at our west facade, which we knew would gain the most amount of exposure, we know that, however, as the sun moves around to the west facade later in the afternoon, the building is already operationally warm. It's already up to temperature. We're in the cooling hours of the building. And we also know we have to concern ourselves with this idea of low angle light. So as the sun comes around from the west, as the angle begins to get lower, we tend to have issues with glare relative to spaces that need a consistent level of lighting for computer use or exam room types and things like this. So this early indicator starts to tell us that on the west side of the building, maybe we don't want to program we're learning this early on, maybe we wouldn't want to program those types of more sensitive spaces along this west wall. So it starts to drive ideas about the program. We then introduce the sky exposure plane, which we need for the setback of the building, and because we have to fold back away from the street facade, we can see that we actually jumped about 20 BTUs additional on this facade footprint, right? So we know that it creates a greater perpendicular condition to the incoming angle of the daylight, which is actually a worsening condition. But we have to do this from zoning because we cannot be in the sky exposure plane. We'd need a variance. We'd have to go through several conditions jurisdictionally to not have that effect happen. As a solution to this, we started to take a look at articulating that facade within the sky exposure plane by creating a diagonal fold along the length of it. So effectively 50% of that wall is sloping out away from the angle of incoming daylight, and 50% is sloping upward. Now we can take a look at a strategy a little bit later, which we did about employing two different types of glazing on this facade to deal with the condition, which partially is spandrel above the ceiling, non-occupied space effectively, that's in that upward sloping zone. And you can see just by doing this, we've re-reduced by 30 BTUs, basically an operational limit almost, the amount of effect on that wall. So here's a basic diagram of this idea of the west facade of the building. On the right-hand side, we're looking at a diagram which says public and office private. Effectively, what we did is we took the public spaces, the transient spaces in the building where people are waiting or only there temporarily, and we placed them along that west facade because we knew that the condition of thermal variation or daylighting variation in that facade could be mitigated with a space which is a little more transient. Then you can see the diagram on the left-hand side is effectively the articulation of that wall, which repeats itself as it goes up the floor. So it not only has a slope backward, the overall facade, it has an articulation through the facade unit itself. Here's the overall strategy for the building, where you can see we have a setback on the ground floor. That's the entry zone of the building. We then have 3 levels of parking, and then we hit our sky exposure plane where we get to the first floor of medical office building and then continue the articulation of the facade up. Here's a view of the overall west facade as it turns the corner to the north. You can see the 3 levels of parking, which sit behind a white perforated metal screen to provide airflow through the building. The storefront on the ground level, which is set back and gets shading from the canopy and the overhang. And then the glass units on the upper floor, which clad the facade on both the north and the west in the articulated fashion. So taking a look at a scenario for how to employ glazing around the facade. We know already that light works in multiple different ways depending on the orientation of the building. So to select one glazing for the entire facades of the building probably doesn't make sense. So we're able to use some tools. Guardian provides a tool called the Solar Performance Calculator, and I'm going to speak a little bit about that, how we developed specific glazing for the facade of this building. We effectively have 3 types of glazing around the building. We have a different glazing on the east with a higher level of visible light transmittance, and then we have 2 types of glazing on the west. We have an upward sloping glazing, which is a high level of reflectivity to inhibit that angle light coming in on the west, but also mitigate glare. Then we have a downward sloping glazing, which has like a higher level of tint, not reflectivity, but that basically follows the line of the low angle light on the west. We can use the Guardian Performance Calculator to start developing different glazing units. We can indicate or try to dial in from some of their standard conditions, transmittance, the reflective value, both visible light in and out, the U value of the glass, and the solar heat gain coefficient of the glass. We can also use that to test multiple manufacturer coatings. You can see here we have PPG type, we have AGC, so we have multiple manufacturers that we can, if we have to base our spec on something that's performative, we know that we're getting a better range of options looking at multiple manufacturers, but that have the similar level of performance, that then develops what you see on the right is sort of a graphic representation of the insulated glass unit with all of the spec conditions for that glazing unit. So we can go straight from the calculator to basically our specified glazing unit. What Guardian then does, which is a very good tool that they have on their website, once you have the glass unit figured out, you can request a Revit family model of that insulated glazing unit that you can replace your standard glass in your default Revit curtain wall with, right? So it builds that IGU based on certain specifications. You load that Revit family back in, and you can sort of replace that entire family to just have that type of glazing. What's nice about that is you can then start to go, and we're in an interior space now, in that west facade, inside one of the waiting rooms, and now we can run and get an understanding of the daylighting illuminance inside of the building. This daylighting illuminance study is just based on the natural daylight coming in. It has no electronic fixtures, no lighting fixtures associated with it. For an interior space, the amount of foot candles, which is the scale on the lower right-hand side, for a waiting space should be about 40, 50 foot candles without any artificial light. If you're doing a task at a table, you might want a task light that takes you up to the 125 range. But you can see, just based on the standard Revit model, this is an illuminance diagram that's based on the standard Revit glazing, which has no properties to it, we're well north of 300, 280 foot candles. And it's a very hot space, as you'd imagine the light coming in there. By getting the Guardian family, it starts to work a little better. And you can see we've been able to reduce down to about 160, but it's still about 4 times higher than we really need to be for the space. So we worked with Guardian and this RGB Value Conversion tool, which basically you can input the transmittance table into this calculator, and it gives you an RGB value for what that transmittance value is. You then you go back into your Revit model, you can create a material that's specific to that RGB value and paint apply it to the surface. Like the inboard light would be the number 2 surface. The 4th surface of glass would be all the way on the inside. So you can apply that specific RGB value to those surfaces of glazing to get the glass to transmit right. You can see we've been able to bring it back down to about the 40 interior range. There's some hot spots on the exterior of the wall, but basically as the light comes through the glazing, you can see it's being diffused correctly in the illuminance diagram. That's a rendering of the final interior space. You can see the level of comfort that's provided, basically. One, diffusing the light so we're not getting glare. You can see the glazing on the top has a slightly different tint, and then the downward sloping glazing, you're able to have views out, but also at the same time it's raking the angle of light, so you're not getting that sharp glare which will come into the space. And then also in some other critical patient units, applying that all the way around the building to make sure that while patients are in a recovery, that they're actually able to have a comfortable level of lighting while they're seated at an exterior wall. So to talk about the geometry of that west wall a little bit, basically the angle is a constantly changing angle from the north, which is the left side of the building, all the way down to the right. It's about 280 feet long. It's 9 bays, about 7 individual units a bay. Now to fabricate that would mean at 3 floors, you'd be about 200 individual unitized frame geometries. Now, I know things are computerized these days, but we wanted to methodize that a little bit to create some consistency. So what we did was we segmented each bay. We created a reveal to allow for the shift change in the angle to happen at each bay. Now, each bay then starts at the same angle and ends at the same angle. That angle is then adjusted a few degrees, which is basically the division of 9 into the angle across the length of the building. We then were able to create some key geometry diagrams, which we, instead of documenting every single bay and every single difference, we created key points and a table to measure the distance from center line of column, from edge of slab, etc. So that working backwards, the surface geometry was defined, basically a matrix. This is only one part of the matrix that you see on the right-hand side. That information was provided to the fabricator. so that they can create their model from that to do the shop drawings. They then provided us back the shop drawings while we were developing the level of detail for the facade, so we could double check to make sure that everything fit within the profile defined geometry, or the design profile of the building. And then in a factory in Croatia, this is fabricated all in Croatia, the individual unitized both the perforated metal panel, which you see on the left, and the curtain wall on the right, was developed. Basically, each folded part was 1 floor tall, and then shipped to site, and then put up in what they call a ladder across the facade of the building. And this is a construction shot from 2 days ago, basically, of the facade under construction.
So we wanted to now take a look at a more suburban model and maybe some of the opportunities that are associated with maybe a little bit of a decompression from a really restrictive urban model. And we wanted to maybe look at that in terms of how architecture can be part of a prescription for care for patients that are being treated here. As we began looking at the Cancer Center project with Indian River, one of the things we wanted to look at was moving beyond this kind of 1980s era, kind of relatively bland beige stucco campus that they had, and looking, rather than looking inward to the campus, look outward to the surrounding area, because it's this really kind of lush subtropical region. There are orange groves, there are preserved public lands around, and so the opportunity was really there to really start to engage nature and the landscape and make that part of the patient treatment process. And so from that, we looked at what's called ecotherapy, which is actually healing with nature, or this kind of idea of the healing process being supplemented and enhanced by this immersion in nature. Everybody is probably familiar with Ulrich's 1984 study into the improvements in outcomes by integrating nature and natural views into the healthcare setting. This is some of the data arising from that. Everything from a decreased length of hospitalization for patients that had this natural view, to decreases in negative comments to nursing staff from patients, and also a less need for pain medications and lesser strength and lesser frequency. So these benefits are really kind of becoming, have been well documented. This is kind of the foundation of today's evidence-based design, and that the data and the research has been just kind of exponentially increasing over the years. Now we know that this kind of access to nature and proximity to nature, it can reduce depression, it can combat obesity. It results in surprisingly improved nutrition just by being close to it. It's reduced cancer risk, lower stress, improved bone density. The list goes on, and it's one of these things where we're kind of getting back to more of the primal roots and the primal instincts of what the healing process maybe once was. And I think it's interesting to note here in Japan, there's a long history of kind of prescribing this integration of nature into a healthcare plan. As a matter of fact, even in modern day medicine in Japan, for instance, if you have a government job in Japan, you're prescribed a forest walk, you actually get a couple of days off from your job just to go and commune with nature and be in nature, because there's an acknowledgement that this really can have tangible benefits to the healing process. As these elements are becoming more prevalent, the evidence of the benefits are becoming documented and accepted, we see a lot of potential for, with very minimal inputs into a project, into a building or a facility, to really have some significant outputs in improvement in patient care. We talked about the reduced recovery time, but a couple of other things when these are really integrated back with the community, and you can let the a lot of programs, especially in the UK and especially in behavioral health, and this started really as almost a hands-on therapy in behavioral health. The evidence was so great in that we're starting to see it expand now into it's very prevalent in cancer, but it's getting much broader than that. But the idea that you can engage the community and create this community of spirit of patients that are embarking on this journey together, and they're helping each other heal, and this becomes a vehicle for that connection. Also, something that we talk about with our clients a good bit is that the idea, if they can create this community spirit of that is actually going out, working on the grounds of a facility and kind of enlivening the grounds through this ecotherapy program, that there's this ancillary property value increase by having on the facility, by having something that's kind of well maintained, loved, and flourishing, rather than putting your building in the center of a parking lot there. And as we started to look at how we could integrate that into a treatment plan, we started looking at these transitional zones between. This was part of a larger campus reimagining. And so not only were we looking at ways that we were kind of treating the patients that were coming just to this facility, but how these gardens could be integrated to those circulation paths between other facilities and future facilities here. We took a lot of time developing kind of the zoning process in this, so that we throw around the term healing garden a lot in healthcare design, and it's kind of become this ubiquitous thing of just a heavily landscaped area that you might be just kind of looking at and observing. And the idea behind ecotherapy is it's much more than that. It's something that's participatory. It's something that brings people back out into the landscape and can become part of that treatment process. Of course, you want the views of this from the interior spaces, but you also want those opportunities to actually get out into the landscape. And so this is just kind of showing some of those zones that we were developing as we go in there. We'll revisit some of these in a few minutes. But this is a quick little conceptual diagram that starts to show how we started to zone the treatment spaces and the functional zones and the patient zones around that access back visually to the outside when you're inside, but also to have those physical connections from those inside spaces back to the outside. So after we started zoning that, we started really looking at building performance. And Tony talked a little bit about some of the tools we use in detail, but this was just kind of the very first solar exposure analysis model that we did on this. And it didn't take a genius to understand that as we, in a subtropical climate like Vero Beach, when our main entrance facade, and where we're trying to capture these views of the orchard, are on the south facade, we're going to have a lot of solar exposure here. For the cancer patient population that was in this building, that became an even higher concern, because there's a lot of sensitivity to sunlight in this patient population. So we had to make sure that we dealt with this in ways that weren't just tuned to energy performance, but they were also tuned to the patient needs in these spaces. So looking a little bit as to what our response was to this, as patients, we mapped the patient movement through this building quite extensively, and we knew the times of days when patients would be coming into the building and occupying certain spaces. This is an outpatient facility, so it's a 9-to-5 building. So we knew that where, as areas were occupied or unoccupied, how we needed to treat the light. So what we did in this 2-story space is we zoned it so that the lower level areas, which you can see that still have the red and yellow highly exposed solar exposure, that those areas were more the incoming patients in the early morning hours when when we got really diffuse sunlight and it was we could protect them from the harsh light there. and, there was a lot of testing coming on there, which you would come in and you get tested, and you would wait in those areas before you went into the infusion spaces. So we knew that those areas were going to be heavy loaded in the early morning to mid-morning hours. As long as we could make it so that the throughput of patients had people kind of cycling through that space and leaving that space before the kind of mid-afternoon hours when the sun really started hitting that would be an effective solution there. So we move up to the second floor, and the waiting spaces that were going to be occupied for the full day, we had we really had to look at it from the full business hours, 9 to 5. So at that point, we started looking at some solar shading elements and ways that we could add this protection while still preserving the views out into the landscape. So you see the section here is showing how those horizontal louvers are oriented there. They're tightly spaced, again, in order to make sure that we avoid that solar glare on the second floor spaces. Again, looking at not only how this performs from a solar perspective and a patient patient comfort perspective, but how do we make sure that the materials and the things that we choose to achieve these are still aligned with that kind of ecotherapy spirit and the spirit of bringing the nature inside the building. So as we look at the material palette, we oriented it to the more natural stones, kind of coral stones and travertine stones, which are very indigenous to that area. The woods that are kind of more aligned with that natural palette. And then also integrating some water elements and some of the actual fauna in the area, so that it becomes very saturated in that. The sky plane, the landscape vegetation on the outside really starts to become part of the aesthetic of what's happening on the inside. And again, as we look at those the shading fins that are providing us the protection on the outside, we also let those shading fins come into the inside of the building and twist around and become, as you're seeing in this rendered view, and become part of the wall finishes and the panels on the inside. They continue on through the lobby and wrap around and become part of the envelope architecture as you move around to the backside of the building. As we developed these strategies, we wanted to start to test how they actually performed. So one of the things that we can do now quite easily is run these simulations throughout the day and start to see how the light moves around the building and make sure that what we're doing really is achieving the desired results. So this animation, I know it's hard to see the movement in the beginning, is mapping the sun moving across through our harshest day of the year. So you see in the beginning that light is completely protected outside that ground floor area, which gets us to about 2 o'clock in the afternoon. So that's when people have cycled through that area. So by the time the sunlight is actually hitting the floor there, that's a relatively sparsely populated area, and the patient population has moved up to the second floor to the patient areas, which are protected throughout the entire day. But you can see here the view through those shading fins is still available to the patients on that second floor. Here's an actual photo of the space as it exists today. As Tony mentioned, our toolbox now to check the effectiveness of these moves it gets a little bit bigger every day. Tony mentioned the very early tools that we have. As we are in design now, we also have this ever expanding tools that we can do as checks through here. These don't replace the more detailed energy models, but they really assist us in making sure that we tune the direction of the design as we go. So this output is just, once we had integrated all those features into the design, we did another checkup of how our energy model was performing. And even though, I will say, 90% of what we were talking about was really in response to patient needs, we get this kind of congruent and synchronistic benefit with the building's energy performance. And I think, again, not to take the place of a full-blown energy model in a test, but the bar I like to point to on this is this little graph in the upper right-hand corner, which is looking at a benchmark comparison. And without even trying, we're bettering the 2030 challenge for architecture in this building and really outperforming ASHRAE 90.1 by over 50%. And just to kind of complete the cycle here and look at the project, we looked at the south side as we turn and look into the infusion bays and the patient zones. That same kind of interior-exterior connection and natural materials and the views of the landscape are still integrated into the design here. And just a few finished photographs of the project. And as I mentioned, as we integrated, the kind of natural elements in the wood across the shading fins and into the interior of the building, where they rotated and kind of became the flat finish material on the walls. It wrapped through the lobby and transitioned back to the outside. And this is also showing one of those kind of pause points in that landscape garden that's through there that becomes more participatory. And one of the big concerns we had at the time was how do we integrate that wood look finish on the exterior of a building in an area which had an amazingly harsh solar exposure in a tropical climate. And the answer for us was Nichiha's fiber cement product, because it really it achieves that kind of natural look and the natural feel of it, even when you get up and you feel the wood graining and texture of it. And it became kind of that perfect completion of this design gesture wrapping the building. So going from looking at kind of more passive responses and how we can tune the architecture, we also wanted to look at some active response products that are available to us today, and for those times when we need something to supplement passive response. So a project that we have going on right now, this project is it's a regional lab for Kaiser Permanente. It's collecting all of the samples through all of their projects in the Mid-Atlantic region, and they come here for processing. So while this facility is not necessarily patient-facing, it's got a lot of sensitive equipment, huge floor-to-floor height, and a lot of office and administrative spaces that are very sensitive to both heat gain and glare as these samples are processed here. So this is, again, an aerial view looking northeast. This low building in front you can see is their existing regional lab, which they have severely outgrown. You can see how much larger our replacement lab is for this. They've outgrown this building so much now that they have some temporary trailers with some lab equipment next to it. This is kind of one of those, it's not quite urban, it's not quite suburban, but so we have a few constrictions that we're dealing here with on the site. The major one is an easement we have to the west here, which is the major power distribution underground electric lines that are running through there that service all of Rockville. So that was a very critical thing that we had to stay away from. Obviously, the existing lab building in the front of the project is going to be repurposed at some point, so we had to stay away from that. You can see the site where the temporary lab buildings are in place now. So while it wasn't quite as constricted of a site, we did have quite a few things that we had to take into consideration as we laid this out. The initial solar exposure here, again, this is kind of showing a split of the building with the images on the far right showing kind of the western exposure, the ones in the center showing the eastern exposure. So those areas were actually pretty easily controllable through passive measures. The eastern exposure, we weren't getting a lot of harsh light, so that light was the solar exposure there and the glare was very easy to deal with. The western facade, as we got to that facade, the angle of incidence was low enough so that with some pretty standard off-the-shelf narrow vertical fins, we could provide that exposure and glare protection there. But on the south facade, we knew we were going to have to integrate something. So the first thing we did was look at some horizontal projections, which, in a typical condition, we probably could have achieved the results we needed. But a lot of the equipment in this building is really, really large. Some of it spans multiple floors, and so our floor-to-floor height in this building is 18 feet. So the cost of projecting the floor lines and the roof lines got to be prohibitive on that. So we started to look at integrating some active systems into the glazing there. So our first kind of analysis of the effect that our passive systems were having, we were getting still about a 60% sunlight exposure, even with that deep overhang, and about a 33% solar heat gain exposure there. So while, theoretically that was okay, we knew we could do better from an energy efficiency standpoint, and we knew we had to do better from a glare standpoint at that point. So we looked at electrochromic or dynamic glass systems as something that we could start to use in there. This was something that would allow the tint of the glass to increase as the solar exposure was increased throughout the course of the day. The particular system that we were looking at was something that had 4 levels of tint, that could come into effect as the sun moved across the facade. Also, as we look at how this is integrated with kind of the concept design in this particular facility. As I mentioned, this is a lab that's processing blood tests, urine tests, and things like that. They're collected throughout Kaiser's region here. So we looked to the test results and what they were doing here as kind of an inspiration to inform the aesthetics of the building. So you can see in the upper left-hand corner, that's a DNA test results. So we looked at kind of that tessellization of that report as something that could start to inform how we articulate the facade here. So, looking at that and looking at the solar demands, we were able to take those inputs and input them into a script in Dynamo that we could then optimize into both a facade pattern that you're seeing on the lower right of this that would inform how the tints come into the program for the dynamic glass, so that we could ensure that we get that performance. We would know which zones needed to tint at which times of the day and which zones wouldn't have to tint at all. And that way, what we were attempting to do with this is to make sure that that even as tints came in with solar exposure, that the patterning of the architecture would stay visible, that we would never have a time of day where the tint would obviate and obscure that patterning that was part of the design. So as we integrated that and we tested the efficacy of those the dynamic glass, the results of this are that sunlight exposure has been reduced from 60% down to just slightly over 1%. And that solar heat gain during the tinted times has been reduced from about 33% down to about 0.4%. So a pretty dramatic increase in performance. Then again, as we look at an animation of how this is working through the day, this is from the outside, and you see those tints coming in, but more importantly, this is from an interior space where we're looking at the efficacy of that glare. So even though this is tinted direct solar exposure, you see that tint comes in and really kind of protects the working environment and the equipment from. So we wanted to wrap this up today by talking a little bit about the kind of importance of, I think we kind of demonstrated from both a design and performance perspective some of the benefits that we can get by tuning the facade to be responsive to the environment. But equally important to that is how we talk about that and communicate that with our clients, and how we put these kind of first cost investments into terms that become easily evaluated in their operational parameters in their business models. So, traditionally we talk about return on investment as a relatively simple calculation, right? How long does it take an investment to pay for itself? That's typically the way we've looked at systems analysis in architecture. In other words, how long does it take, if I spend X amount of dollars on an increased energy efficiency for a system, how long does it take me to gather the energy savings to pay for that system? Right, and that's it's a very valid way to look at it, but it's also not really aligned to the more complex and more relevant issue of how the client is going to pay for this investment. What impact is this investment going to have to their operational model? A recent illustration of this strategy is a project we're currently working on for Greenfield Hospital in New Jersey. We knew that in order to create a sustainable business model for our client, we had to create a platform that was very energy efficient. So the first thing we did in this analysis was look at what they were currently paying for energy. And surprisingly, in the Northeast, they had a pretty good negotiated rate that they were purchasing energy for. And that's the top figure there. It was kind of right in the middle of the national average in that $5 to $6 range per square foot on an annual basis. So once we had that information, we were able to look at what their net operating income environment looked like, how profitable were they currently. We were able to apply a target energy reduction to these calculations. You see in the notes down here, one of the things we started looking at was about a 35% target for reduced energy cost. So once we knew what energy cost and what their operational model was, we could start to look at what that really meant to their bottom line. And what we found is that for every dollar they were spending on energy, they had to deliver $26.39 of billable services to their clients in order to gain the offsetting revenue for that. So what that means on an annual basis is if we can achieve that 35% energy reduction, they're going to save over $900,000 a year, which equates to over $24 million in revenue that they don't have to generate just to pay for the energy. Or maybe a better way to look at that is that's $24 million a year that they can put back into their mission, which is patient care, rather than having to buy energy with that. After that first exercise of kind of building the construct and gathering that data, and we did that before we even won the job, when we were pursuing the job, soon after we started design, we started modeling what the actual application of these things looked like. So you can see here in this chart, we started looking at what the national average is for hospitals in the country, and you can see our hospitals in the United States are performing just awful, at an energy use index of about 249. And that's not only an indication of the aging infrastructure in the healthcare industry, but it's also got to do with the fact that hospitals are energy hogs. They operate 24/7, 365. They have a lot of process loads, plug loads, and it really stresses the importance of the physical plants, the central energy plants that we need to create to service these things. That really drives efficiency in this industry. So we started dividing this up into the different components that we needed to analyze in order to deliver the most efficient system. And again, that's the central energy plant that's going to service the campus. What's the building distribution system going to look like? And then what's the architecture going to look like? Those passive and active systems we've been talking about that contribute to the energy performance of the architecture. So with those three things in mind, we started to scenario test some various options for performance. Baseline is simply that. What's code minimum here? That's option one, and it's just conforming with ASHRAE 90.1. And the headline there is, even if we just do a code minimum now, we're bettering the average hospital performance by about 13%. So you got a head start just by meeting code. But we started mapping those higher efficiency systems like distributed heat generation for the central energy plant, enhanced heat recovery, ground-coupled heater and chiller plants were several options that we analyzed. Then for the building mechanical distribution system, we started looking at dual outside air systems, displacement ventilation, and radiant panels that were distributed in more saturated areas depending on the program. And then for the architecture, we started targeting, we hadn't really started designing the building yet, so for these, we targeted percentage improvements over that ASHRAE standard. And so as we worked, this was an integrated project, and so we had great engineers and construction managers on board. And the surprising thing to us is when we started analyzing what the real costs of these systems were, what we found is option 3, which was performing at a 59% rate, was able to be achieved for not much more first cost than option 2, which only was performing at 49%. And when we looked at what the total construction cost was for that of $2.59 million, and the energy savings associated with that of $909,000 a year, which is again equating to that $24 million in revenue billings that they wouldn't have to burden their clients with, or that they would be able to direct toward client care. The return on investment for this was really, really quick. It was under 3 years. So it became a really easy thing for our client to make a decision to invest the money in this more efficient system. And it's also an illustration of the power of this type of communication, because once they saw these benefits, they went even further with this to the point where we're now, as we're in construction, we're starting to integrate renewable resources, photovoltaics, some hot water, solar, and things of that nature that are going to make this even a more efficient platform.
So with that, I want to thank everyone, and now we can open it up to Q&A.